Hello, welcome to lecture 8 of Elec Eng2CI5. In this lecture, we just go over some examples that summarize different aspects of circuit simplification approaches that we learned so far. The tools that we have in this course, in this chapter, that we address in this chapter, series connection, parallel connection, using Ohm's law, using delta to Y connection, and using power conservation. Okay, so of course in addition to that we have current division and voltage division. So these are the basic rules that we have. We can use them to simplify any circuit and to calculate the currents and voltages everywhere in a circuit. Okay, so we'll address three examples in this video, and we'll take it from there. Okay, we have this circuit here. We have three sources, V1, V2, and V3. And we have a large number of resistances. We are asked to calculate the total resistance seen by the sources. It's called here R total. We call it R input or R equivalent. They are all the same. So we'd like to calculate the input resistance seen from the source side. So this whole circuit can be replaced, all the resistances can be replaced by one single resistance connected to one single source. Okay, so this equivalent source, we call it Vs or V equivalent, and the total resistance is called, you call it here RT, but it can also be called R equivalent or R input. We would like to determine the power supplied by that equivalent source. Would like to calculate the total current drawn by the circuit. So there will be some current that's drawn from the sources. So this current maybe will flow this way. We can call it here, I call it I total, the total current, IT here. Okay. We can also find they are required to find the voltage across the V11, this V11 across R11, the resistance R11, and also the voltage difference VAB. So this is point A and point B, and would like to calculate the voltage difference VAB. Now the circuit as it stands, it looks a little bit scary, but it's not really that difficult because there are many simplifications that you can make before you do any calculations. So we do these simplifications, we redraw the circuit, the circuit will look way simpler. So let's see. We can see that these two resistances are in parallel and they are series with this one. So this branch will give me one resistance, okay, one equivalent resistance. This one in series with the parallel combination of these two. But this whole branch is connected between this point and this point. So, but these 2 points are shorted by this piece of wire. So this whole branch will disappear. I don't need these resistances in my circuit. They do not contribute anything to the circuit because they are shorted out. So you can see this whole branch is connected between this node, and it's being shorted by this piece of wire. So I can redraw the circuit and eliminate them. This resistance R13, its other end is hanging in the air, so there can't be any current flowing here. So this resistance also is not part of my circuit. Okay, let's take a look. We have here R9. It's obvious it's parallel with R10. Okay. But what may not be that clear is that this point is the same as this point, is the same as this point, is the same at this point. It's the same at this point as well. So this means that R9, R10, and R11, they share the start node and they share the end node. Okay? So R9, R10, and R11 are in parallel. Okay? Okay, what happens to R12? R12 is connected between this node and this node, but these two are shorted, as you can see. So R12 will disappear from my circuit. So we can immediately say that this branch is gone. I don't have this branch anymore. I don't have this resistance anymore. Okay, and I'm gonna replace D3 here, the three resistances, by one resistance. What is the value of this resistance? This is 10K in parallel with 10K will give me 5K. This combined 5K is in parallel with 5K will give me 2.5K. I have as well R7 and R8 are in parallel. Remember, this is the same node. Okay, so this is 5K and 5K. This will give me 2.5K. 13K will still be the same. 12K will still be the same. Here we have three sources. This one is trying to push current this way, 44 volts. 15 volts trying also to push current in the same direction, while 17 is trying to push current in the opposite direction. Then if you go around in this loop, you'll see that the net voltage will be 44 plus 15 minus 17. And this voltage is trying to push current in the clockwise direction. Okay, so all these changes, you can make them immediately. Replace these three sources by one source. Replace these two resistance by one resistance 2.5K. Replace these three resistances by one resistance 2.5K. Eliminate this branch, eliminate this resistance, and redraw the circuit, and the circuit will look way simpler. Okay, so we drew the circuit now, and you could see this is how the circuit looks like. These are the three resistances in parallel. These are the two resistances in parallel. This is the equivalent source. It is the sum of the three sources, and this is what I write here. This equivalent source is V1 plus V3 minus V2. V1 and V3, they are helping one another. They are trying to push current in the same direction, whereas V2 is opposing them. So 44 plus 15 minus 17 will give you 42 volts. Now, from this circuit, we can see that the resistance seen by the source, of course, you can do it in the way we learned in class, but I can immediately see the result. These three are in series. So this will give me 18K. This 18K in parallel with 12K. And this whole net resistance is in series with 6.8K. Because any current will flow this way, and then it will split through these two branches. So this is how we write it. Of course, you are welcome to do it step by step. You can make this one 18K, and then you put it in parallel with 12K, and then you draw another graph where 6.8K is in series with this parallel combination. I'm used to do that in a little bit faster way, and probably you'll also by the end of the course you learn how to do it in a faster way. So this is how I write the equivalent resistance seen by the source. It's 6.8K in series with the parallel combination of these two branches, which is 12 kilo ohm in parallel with 18 kilo ohm. And this is what I write here. This is the meaning of this expression. 6.8K in series with this combination. What is this combination? It's 12K in parallel with 13K plus 2.5K plus 2.5K. This will give me 18K. Then I have 12K in parallel with 18K. This one is in parallel with this one. Okay. If you do this parallel combination, 12 by 18 over 12 plus 18, you get 7.2K. Then the total resistance seen looking into from the source side, the equivalent source side, is 14 kilo ohm. Okay, so we know that this whole circuit represents the resistance of 14 kilo ohm. Once we have found the resistance, we know everything. We can get the power supplied by the source. We know the voltage of the source. We know the resistance seen in the circuit. So we can say that the power is equal to the voltage squared divided by the resistance. Okay. We can also get the current I total, the current supplied by this equivalent source, because this current is nothing but this 42 volts divided by the total resistance which we just calculated. So this can be found. So once you found IT, you can use current division to find the I3 and the I2, because you can see I3 will be divided into one current flowing in this branch and one current flowing in this branch. Now you should notice that I3 is flowing from the bottom node to the top node, while the current supplied by the circuit will be actually flowing from the top node to the bottom node. So when I include I3, I must take this into account with a negative sign. Okay, we start to do the calculations. We know the equivalent voltage. The three sources represent one source, 42 volts, and this 42 volts sees the resistance of 14K. Then the power supplied is 42 squared over 14K, and I put it as a positive number, and I write with it supplied. Of course, if you are doing conservation of power, this has to be included as a negative power, okay? Because it's not power absorbed. But here I'm just doing calculation of the input power. I'm not applying Telegraph theorem. So this is why I did not really worry that much about the power at power sign, as long as I understand it is power supplied. It's not power absorbed. Okay, now this is 42 volts, this is 14K. This is how the circuit really equivalent looks like. So I can get the current IT, and the current IT will be flowing this way. Okay, so IT is simply the current supplied by the source is the equivalent voltage divided by RT. So 42 over 14K will give you 3 milliampere. Okay, and I redrew the circuit here just to make it simpler for you to see what's happening. This current is equal to 3 milliampere. Will split into two currents. One current will go into this branch and another current will go into this branch. These two branches are in parallel. They are connected between node C and node A. So I can get I2, this current here, current division expression. I2 is equal to IT multiplying 12K over 12K plus 18K. This is the whole resistance of these branches are 18K. So I2 is equal to the total current, which is 3 milliampere, multiplying 12K over 12K plus 18K, get 1.2 milliampere. Now, what about I3? I3, again, I can calculate it. It's going to be a division ratio. It's 18 over 18 plus 12. But I must include a negative sign. Why? Because if IT is positive and flowing this way, I3 will be actually flowing from top to bottom. It's going to be flowing back, downward, okay? So this is why I include this negative sign to show that the actual direction of the current is opposite to the reference direction I assumed in the beginning, or the reference direction I was asked to calculate. They asked us to calculate the current flowing in this direction, but the current flowing in this direction will be minus this calculation minus 1.8 milliampere. So 1.8 milliampere are actually flowing from C to A through the 12 kilo ohm resistor. So this again current division ratio, okay, but I took into account the direction of I3. Okay, we still have to find two things. We still have to find the voltage VAB, and we still have the voltage across the resistance R11. R11, if you remember, R11 was one of three resistances connected in parallel, and they were connected between points D and E, and their net resistance was 2.5K. So this voltage here is the same voltage across R11. It's the same voltage across the other two resistances, but we combined all three resistances into 2.5K. This has to be very clear in your mind. Now, I mentioned to you in class, in order to calculate VAB, the voltage difference between A and B, you have to find a path along the circuit. Take any path that you like that connects point B to point A. So I have to go from here to here. I will take this path here, okay? Of course, you are most welcome to go around. Maybe you can take this one to verify the answer. Or you can go this way. Okay, all of them should give you the same answer. Okay, I took the shortest one. This is the shortest one. So I move from node point B to point A, and I will add the voltage drops that I see them. If I see negative, positive, this means that this point higher than this point, and then I have to add that voltage. If I see positive, negative, it's going to be negative. So from here to here, I could see a positive increase. So this is I2 multiplied 13K. From here to here, because of the assumed polarity of I3, you notice even though I3 is negative, but it doesn't matter. I'm assuming it to flow this way. Then the drop resulting from it will be plus minus. This drop will be negative. This is okay. The equations will take care of themselves. So VAB is equal to I2 multiplying 13K plus I3 multiplying 12K. Negative, positive, negative, positive. Okay? But when I substitute for I3, I'm going to use minus 1.8 milliampere. Okay? So the reference is what matters. You assumed it to be flowing this direction, then the drop resulting from this current will be positive, negative. So when you calculate VAB, you move from B to A and you add the voltage drops. Negative, positive is positive, positive, negative is negative. So this is from negative to positive, so this is a positive drop, I2 3K. Negative to positive, then the positive drop, this is I3 multiplying 12K. And then later when I substitute, I take into account that I3 is actually flowing in the opposite direction. Don't do double negative. Okay, you assume you have a reference direction, use that reference direction. Okay, so you calculate this term here, this will give you 15.6 volts. You calculate this one, this will give you minus 21.6 volts. The net result is minus 6 volts. To calculate the voltage VDE, the voltage VDE is simply the voltage drop across the 2.5K, and you have a current I2 is flowing this way, so it will be actually positive, and the value is I2 multiplying 2.5K. So this drop here, VDE, is the voltage across this resistor. The current I2 we know is 1.2 milliampere. Then the voltage is I2 multiplied by 2.5K, 1.2 milliampere multiplied 2.5K. This is not 25 here. Let me correct this typo. This is 2.5K, and this will give you here 3 volts. Okay, let's take a look at another example. We have this circuit here, and would like to calculate the input resistance seen by the source. We have here one source. If we had multiple sources in this branch, we'd have replaced them by a single source because they are all connected in series. But here we have only one source, and would like to calculate the input current IS, the current supplied by that source. So the input resistance, we call it R equivalent, or R input, or R total. And the supplied current by the source, we call it I source, or I in, or I total, or I equivalent. It has many names. They all mean the same thing. It's the current supplied by the source. Now, if you take a look at this circuit, you will see that you will have difficulty simplifying it. Why? Because you don't see any single parallel or series connections. This resistance, for example, is not in parallel with this one. This branch is not in parallel with this one because you have this current here flowing out. So these are not in parallel, and these two are not in series either because you have this branch as well. The same thing can be said about these two. So in order to simplify this circuit, we can use the Y to delta. So you can see here these 3 resistances, they all connected to this central point. So this looks like a Y connection. Okay, so you can define the points. A point, name them A. These point nodes, give them A, B, and C, and then connect them with resistors, and then try to find these equivalent resistors. So we're gonna now be using a Y to delta connection in the hope that you can break this circuit into series and parallel connections. So let's see how this is done. So when you apply the Y to delta connection, so you have to name a node A, you name the other node B, you name the other node C. Okay, the resistance corresponding to A in this triangle. This is a triangle here. Okay, 3 edges. Is called R3. So corresponding to A is R3. Corresponding to C is R2. Corresponding to B is R1. The order here matters because the formula given in the book will depend on this order. So once you name this A, B, and C, so this one will be R1, this one will be R2, this one will be R3. R3 is the one facing A, R1 is the one facing B, R2 is the one facing C. Okay, the formula for transforming from Y to delta is given by this expression, and you can see because R1 is facing node B, I divide here by RB to calculate R1. Okay, this is called RA, this is called RC, this is called RB. Okay, so I calculate that, so I multiply 10 by 5, 10 by 20, and then 20 by 5. I sum the product of these 3 resistances in pairs, and this is what I get here. And then to get R1, I divide by RB. To get R3, I divide by RA, which is 10 ohm. To get R2, I divide by RC, which is 5 ohm. Okay, so if you do that, you get R1, 10 by 5 plus 10 by 20 plus 20 by 5. So you get this expression, you divide by RB. This is RB. It is a resistance connected to node B. It's 20 ohm. So you get 350 divided by 50. You get by 20. You get here 17.5 ohm. So we know that R1 is equal to 17.5 ohm. You repeat the same expression again for R2 and R3. The only difference is that for R2, you divide 350 by 5. So this will give you 70 ohm. Okay, and then for the third resistance R3, you divide the 350 by RA, which is 10 ohms. This gives you 35 ohm. Okay, so now once we have done that, we remove RA, RB, and RC and replace them by R1, R2 and R3 and see how the circuit is simplified. Okay, so we completed our solution. We found R2, as I said, R2 we divide by RC in the denominator. You get 70 ohm. R3 is the one facing node A. So divide by RA, which is 10 ohm, you get 35 ohm. So this is now how the circuit looks like after we simplified it. I did not show the source. Of course, the source is connected here because I'm only calculating the input resistance for now. Now the circuit is way simpler. Why? Because I can immediately see that I have 70 ohm in parallel with 30 ohm. These two are the same node. So 17.5 ohm is in parallel with 12.5 ohm. These two are the same node. So 35 ohm is in parallel with 15 ohm. So I can draw the circuit in a much simpler way, and I will have only three resistances. This parallel combination, this parallel combination, and this parallel combination. Remember, this equivalent resistance here is in series with this equivalent resistance. Okay, so let's take a look at the circuit. I now start to combine these resistances. I had here 30 in parallel with 70. So this will give you 30 by 70, or 30 plus 70 will give me 21 ohm. I have for this one here 17.5 in parallel with 12.5. So 17.5 multiplied by 12.5 over 17.5 plus 12.5 will give you 7.29 ohm. The numbers not always work out to be nice, so not in all examples. So here, remember, I forgot to put ohm here. The same thing is happening for R3. I used here notation R1, R2, and R3. I should not have done that because I'm confusing it with the delta connections. These are different notations. You can call them R dash, R double dash, R triple dash. It doesn't really matter as long as you know what you're doing. Okay. So now I had two parallel resistance in the previous slide, 15 in parallel with 35. 15 by 35 over 15 plus 35 will give you 10.5. So this is what we have here, and this is, of course, is in ohm. Okay. So now we have, okay, we have one last example. We have here this circuit. We have one source, we have a number of resistances. We are being asked to calculate the current IT supplied by the source. This is the current supplied by the source. Find the currents I1 and I2. Find the currents I3 and I4. Find the voltage difference VAB, so the voltage measured between these two nodes here, and the voltage VAC between these two nodes. At the first look, the circuit looks scary, looks a little bit complicated, but actually it isn't. It's actually a very simple circuit. Why? If we realize that this node is the same as this node because they are shorted, and this node is the same as this node because they are shorted, you can see that this branch is in parallel with this branch, is in parallel with this branch, is in parallel with this branch. So we have effectively 4 branches in parallel. But the circuit is drawn in such a way, in a confusing way a little bit, okay? But once you realize that this node is the same as node A, as this node is the same as node B because they are shorted together, so this means that I can redraw the circuit in a way that's similar for me. Remember, these two are, now we start to do some simplifications. 390 ohm is in series with 910 ohm, so this will give me one resistance which is 1300 ohm. 180 ohm is in series with 440 ohm. This will give me one resistance of 400 ohm. I can of course combine these two as well to give me 710 ohm, but I will not do that. Why? Because I need to calculate VAC. So I would rather draw them again as two separate resistances. Okay? If I can, I understand that the total resistance of this branch is 710 ohm, 560 plus 150. Okay, so when you draw the circuit, this is how the circuit really looks like. You have 400 ohm in parallel with 1300 ohm, in parallel 710 ohm, in parallel with the source branch. Okay, now it looks way simpler. I know that from this side, I see 3 resistances in parallel. 400 ohm, 1300 ohm, and 710 ohm. I can use the expression for parallel resistances. that 1 over R parallel would be equal 1 over 710 plus 1 over 1300 plus 1 over 400. And you can inverse them, inverse these quantities, you sum them and you take that inverse, you end up with 213.8 ohm. So now this whole circuit can be replaced by the following, by 100 ohm in series with this RB. So maybe I don't have enough room here, but maybe I can draw it in this part. So this is really what I have right now. I have a source, I have 100 ohm, and it is in series with RB. Okay, this is 100 ohm. And this is my source, which is 20 volts. Okay, so what is happening now is that the total resistance seen by this source is 100 ohm plus RB, which is 213.8. So the equivalent resistance seen by the source. So remember the source from this point, between these 2 points, it sees 100 plus RB. Okay, so you sum 100 to RB, you get 313.8 ohm. So what this means is that now I know the input resistance, I can calculate the current supplied by the source IT, because between the two nodes of the source, I see a total resistance of 313.8 ohm. Then the current IT drawn from the source, even from this diagram, I can calculate this current, is 20 volts over 100 plus RB. So it's 20 over R equivalent. So 20 over 313.8, you get 63.7 milliamperes. So we know that the total current flowing here, and remember these two currents are the same. The current flowing here, I total, is the same current flowing here, it is the same branch. So this current I total will flow this way, and then we'll split into I1, we'll split into I2, and then I2 will split into I3 and I4. Okay, so now what remains to calculate the currents is to do a number of current divisions. I have I1 flowing in, I have I total flowing in, it will split into I1 and I2. With what ratio? Well, I have first to find the parallel equivalent of these two. The parallel equivalent of these two resistances are in parallel, and they represent one equivalent resistance of 305.8 ohm. Where did I get this one from? I multiplied 400 by 1300 over 400 plus 1300. So now when I calculate I1 and I2, I'm doing a division ratio between 710 ohm here and 305.8 ohm here. Remember, when we have multiple resistances in parallel, we have to find this equivalent. We have to treat them as one equivalent. If you want to get the current I1, then I1 is this R equivalent, R resistance here, or R the parallel combination of these two resistances, divided by this parallel combination plus 710. And this is what I have here, is simply a simple current division. So I1 will be equal to the total current flowing in, which is 63.7 milliampere, multiplied by 305 over 305 plus 710. And this is what I have here in this expression. And if you calculate this one, you get 19.18 milliampere. Of course, you can get I2 through a current division. So you can say that I2 is equal to I total multiplying 710 over 710 plus 305.8. But I found it easier to apply KCL, so I said that I2 is equal to I total minus I1. Because remember, I total is equal to I1 plus I2. So I use that in the next slide. So I move to calculate the other currents. So I found I2. I2 is equal to I total minus I1. I have already I total 63.7 milliampere. I calculate I1 using current division 19.18 milliampere. If you subtract them, you get I2, which is 44.52 milliampere. So when you sum I1 and I2, you end up with I total. Okay, now I2 will split again into I3 and I4. Why I'm doing all these calculations? Because I need to calculate voltage drops. So I need to know the currents in all the branches. Okay, this is why I'm doing that. So I can get I3. I3 is equal to I2 multiplying 1300 over 1300 plus 400, and this is what I have here. I2 is this amount, which is 44.52 milliampere. You multiply by this ratio, you get that I3 34.04 milliampere, and it's expected that the 400 ohm will get most of the I2 current because it's smaller, way smaller than the 1300 ohm. Okay, now we can get I4 by saying that I4 is equal to I2 minus I3. Remember, I2 split into two currents, I3 and I4, and the sum of I3 and I4 will give you I2. So I can simply say that I4 is equal to I2 minus I3. I2 already calculated is 44.52 milliampere. I3 we calculated using current division, 34.04 milliampere. Do the subtraction, you obtain 10.48 milliampere. Okay, now we are all set to calculate all the voltage drops. I need to calculate VAC, I need to calculate VAB. You can see VAC is the voltage drop across the 560 ohm. So, and the current is indeed flowing in the shown direction. So the current will flow from A to point C, okay, and it will create this polarity here. So VAC is the voltage across the 560 ohm. So it's I1 multiplying 560 ohm. So if you get I1, which we calculated earlier, okay, and you multiply it by 560 ohm, I1 here, I believe it was 19.18. So 19.18 you multiply by 560 ohm, you get 10.69 volts. Now if you want to calculate VAB, so the voltage difference between here and here, we can do it of course in the way we learned in class. You can take any contour going from B to A and you sum the drops. You can do it from here to here, and I encourage you to do it from here to here. I encourage you to do it from here to here, and do it from here to here, and get the same answer in all branches. It's a very good exercise. I'm a little bit lazy, so I'm gonna go from from point B to point A through this branch. So you can see I have two drops, negative, positive, so this will be counted as positive. This one is negative, positive will be counted as positive. So I have 1 multiplied 560, I have I1 multiplying 150. So I1 will be multiplying their summation, which is 710 ohm as shown here. You obtain VEB, which is 13.6178 volts.